Okay, so let us continue with the last topic. So we are having two tracks, okay? The slides that we are doing for the class that will go on in one direction. This we will have the continuity with the previous video, okay? So slides and classroom we are doing separately. Content is the same in theory, okay, but in the examples and in the discussion we will do different things, okay. And here also, for example, we will do different circuits than what we did in the class, and some topics like layout, inverter threshold characteristics, etc., it is more easier to follow in these videos. So it's up to you, but from our side the recommendation is only one is not enough. Imparters is also good, classroom discussions are also good. Especially classroom discussions are good because you can ask questions there, you can test your understanding there. Here this is one-way communication, we can only talk and record it and you have to watch it later. But classroom, as you have already experienced, is two-way communication, okay. So we will continue with the last topic that we stopped in the videos. We discussed how to design compound gates, that is not the basic gates. Basic gates we have NAND, NOR, etc. And just to recall two important points, okay. First point is with respect to the series parallel connections. So series parallel connections, we know that if the terms are in series in the function, okay, that is I have okay, this is what we do. I have two terms and they are being ANDed, and these two terms, they not necessarily, as you know by now, not necessarily single terms. It could be a more complicated term like AB plus C, etc. But what that means is the two terms are in series in the NMOS network. And similarly, instead of AND, if you have a plus, okay, that means that the two terms are in parallel in the NMOS network. This is the first rule. The second rule is, once we have finished the network for the pull down network, the NMOS network, just make it opposite for the pull up network. These are the only two rules you remember for any gate, that is any compound gate also. So we'll look at some examples. First example, okay, AB plus CD, the whole bar. And anytime you have a function, you have to make first one decision. What is that decision? Sum of product or product of sum. If it is sum of products, okay, your pull down network is going to have many parallel branches. How many parallel branches? How many ever sums are there in your function? If it is product of sum, your pull down network is going to have many series networks. How many series networks? How many terms are being producted in your function? So we have a function. This is in SOP or TOS form. That is the first question. This is in sum of products. There are two sum terms, okay. So if you are drawing the pull down network, two terms. So in the pull down network, output pull down network is going to have two parallel branches, and each parallel branch I have to implement the term within the function. So okay, so AB plus CD, AB plus CD. This is the pull down network. Once this is done, don't have to look at the function anymore. Just make the opposite as the pull up network. So two branches in series, two branches in parallel, which means two branches in series. Okay, and within that also they are in series, so they have to become parallel. Okay, and on top power supply VDD. So this basically is a circuit for our function. And one more thing, we mentioned this also, but all these are naturally inverting. So even though there is a bar here, okay, automatically the bar will come. We don't have to add an inverter at the output node. So this basically is another thing to remember. Okay, just because the bar is there, don't add an inverter here. The bar comes with the nature of the circuit. The nature of static CMOS design is whatever functions we are implementing, they are implemented in inverted form. If you want the non-inverted form, then you have to do some extra work. Okay, and that is why in our gates also, among the basic gates, we have not done AND OR. Okay, we did only NAND and OR because they are the ones that are naturally occurring. Now you can go back even more to your digital design, or even before that, you might have read somewhere that NAND and OR gates are more simple to implement compared to AND OR, right? And or are not considered as basic gates. For example, NAND is a basic gate, AND is not a basic gate, right? That is because NAND actually is the one that comes directly from static CMOS circuit, not AND gate. And AND gate is almost a basic gate, but only thing that we cannot do with AND gate is we cannot do inversion. With NAND gate, we can do inversion. Okay, so some other things that you might have learned before. The reason for that is because of the nature of static CMOS circuits, they are naturally inverting. Okay, so we'll do some more examples. Okay, so one more example. As always, start with the pull down network. Sum of product or product of sums. That is also is the question. Here we have two terms that are being producted with each other. So this is a product of sums. Okay, which means that it is only going to have one branch in the pull down network. One single transistor. If I write like that, what should be the input to this transistor? Definitely it will be D. Okay, and then I have A plus B plus C term. Whenever I have plus, it means that okay, A plus B plus C. So this is the pull down network for this function. Then look for the pull up network. Make this the opposite. So on top I will have VDD, and I have two parallel branches. Here A, B, C are in parallel. So if you're putting that in the parallel brancher, don't put it directly as parallel. Okay, they should become series. So here A, B, C. Okay, this is the implementation, but still something is remaining. We have not completed it. It is in non-inverted form. So whenever we have a function that is a non-inverted form, we have to add the inverter. Where to add the inverter? To the output. This is basically at this point A. Okay, this is the function that we have here. So give that to a inverter. Okay, and this is the required function f. And again, we have mentioned this also, but generally in static CMOS, when we say give it to an inverter, you might ask where to give it. Okay, always the inputs are given to the gate terminals. Inputs are not given to source or drain terminals. Output are taken from the source or drain terminals. Input signals in static CMOS at least are always given to the gate terminals. Okay, so we take the output and we give it to the gate terminal of the PMOS and NMOS, which is the inverter, and we get the output, whatever function we want. Okay, so this is one example. Okay, so nothing to explain, same old rules, nothing new. A, B, C plus D function and the inverter together will give you the function. Okay, so there's a couple of more examples, you can try those in the slides. Okay, so one example I wanted to try. Okay, so this, I'm sure you are familiar with this expression. This is our Xor function. And XOR gate is very important in digital design. Can you tell me the reason why XOR gate is very important in digital design? There is no digital design in the world without a XOR gate. Okay, and the reason is XOR gate is one of the key components in implementation of digital adder. Okay, next unit we are going to be looking at addition, binary addition, but there is no circuit in the world that can do binary addition without a XOR gate. So XOR gate is one of the, it's as important as a basic gate, because somewhere during the calculation of the sum, okay, the XOR term will come into the picture. So we will look at the circuit. And also I have added this because it's not a very complicated function. It's much simpler than many of the other functions also that you have done. But only difference in this particular case is there is a bar. Okay, so a simplifying assumption for you, if you have any function, okay, not only XOR, any function with a complemented signal, assume that it is available to you. Okay, it is making your life easier. You don't have to give, we know how you can generate it. Give it to an inverter, give A to inverter, you will get A bar, but you don't have to show all that. Okay, just assume that the complemented signal is directly available. So I will draw this thing for this XOR gate. Okay, so just directly assume, you don't have to worry about showing how A bar and B bar are generated. It's not very complicated at all. So directly assume those signals are available, A bar, B bar, B bar, A bar, and don't forget the inverter. If you don't use the inverter, you are getting the XNOR function. XNOR, give it to inverter, you get a XOR. Okay, so one last this thing. Okay, so this time I wanted to show this function to see if I wanted to basically compare two different implementations and compare the number of transistors in each of those. So this is the function, but another way to write it is equal to A B plus C into, let us compare for each separately how many transistors we are getting for the circuit. Okay, so first one, I'm not going to do it. Okay, I'm just going to write the number of transistors. For the first one, can you tell me the number of transistors? Can we work that out? Basically, we will start with the pull down network. Okay, and the pull down network is in sum of products form. So there are three sums, which means there will be three branches in parallel, and each branch will have 2 transistors. So 2 plus 2 plus 2, that is total of 6 transistors for the pull down network. Pull up network will also have the same number of transistors, 6. Okay, so 6 plus 6 is 12. 12 plus 2 is 14 transistors. What are the two last two is for inverter, because if you remember, this is the expression for carry out. Again, we are talking about the digital adder, 1-bit adder in particular, full adder. Okay, AB plus BC plus CA is the expression for carry out. So if I do it directly, I will get 14 transistors. I will do this bottom one, okay, and see how many are coming. AB plus C into A plus B. So AB on one side, and C into, again, I'm being a little lazy. I shouldn't mix uh, logic and circuit symbols, because this is circuit. This is a gate level or logic symbol, but since we all know very well static CMOS inverter, I don't want to draw the whole thing. But how many transistors here? 1, 2, 3, 4, 5. So 5 twos are 10 plus 2, 12 transistors. Okay, so this you have to remember in the exam also. If you can simplify the function, okay, and say by factoring out a term or something simple, nothing too complicated, you are supposed to do that. Don't draw directly for this one. Okay, you will get some marks, but it is not the best implementation, to be on the safe side. Okay, please try to simplify the function itself. It's also the natural thing to do. It's also the practical thing to do. Okay, don't go for the complex function, go for the simpler function. Okay, so another interesting function, basically there's nothing in it. The function doesn't have anything, but it is still required to implement it. And suppose I say, just put a wire, right? Y equal to A. So why are we trying to use some gate when I already have the input, and the input and output should match each other? So just connect it with a wire. So connecting it with a wire will match, but whenever we have this, okay, what that means is we want the input to get somehow restored to a perfect value, and we'll talk more about this towards the end of this unit. But there are many circumstances where the signal, right, for example, I have This could happen. I can even show you many simulation waveforms where this happens, right? Because the signal is generated from many parts of the circuit, and two ways this could happen. Okay, some parts of the circuit are still generating the correct value, and when they are ready, then it goes from 1.7 to 1.8. This is one case, but the more common case is when the signal, okay, is being affected by some amount of noise, and in that case it might change from its perfect value, because there is noise everywhere, right? Even in nature, for example, we have water, we have air. There are sources of pollution, meaning that the air gets contaminated with some particular this thing and it loses its pureness. The same thing can happen for electrical signals. Electrical signals, generally we will try to insulate them. So for example, if you have a wire going like this, right, and the wire is insulated with a this maybe rubber or something like that. But in VLSI circuits also there is insulation. But unfortunately, the substrate, in this case, the wire is sitting on the wall, right? And between this wire and maybe the wire on this side, there is too much of separation. So there can be no interconnection through the wall. But if you look at VLSI circuits, the separation between wires is very, very low. So even though they are sitting on the silicon substrate, even though they are insulated, because the separation is so low, right, they can talk through the substrate. So if some neighboring circuit, some change is happening, my wire, which is supposed to be at a constant value, can get affected. It can get pulled up or pulled down, mainly because they are all interconnected capacitively. And that is the reason why this could go down from 1.8 to 1.7. So I want this is my input. I want this to get transformed to a better value. Throughout I want it to be 1.8, and that is why I am putting buffer. If you simply connect the input to the output through a wire, there is no use, because the signal has not improved in the quality. So this is not a useless function, this is very useful. And how can we get this? Okay, very simple. We have our static CMOS inverter. Okay, connected to two back-to-back inverters. So the imperfect value, okay, gets perfected, and this is also example of a particular circuit called as a buffer, and we'll discuss more about this because buffer is very important, especially since we also discussed in terms of practical job descriptions in VLSI domain. One of the most important descriptions I mentioned was physical design. Physical design is responsible for the circuit, responsible for the design at the layout level. Okay, and layout is the final step before fabrication. The maximum amount of timing information is available at the layout level, and there if you check and the timing is not being satisfied, you can insert these buffers to improve the timing. So that is another functionality of buffer. So we have only discussed 2 or 3 functionalities. They are very important circuits, especially for physical design engineers. Their best friend is the buffer. Okay, and whenever they insert a buffer, we will also see, it sounds quite magical now, but as we will see from the equations, as we will see from the analysis of the design, buffers can actually improve the timing by a very great amount. Okay, so this is the very simple circuit. You can have multiple ones also. There is no reason why I didn't put 4. I can put 2, I can put 4, I can 6, any amount I can put to design what is called as a non-inverting buffer. If you put odd number of inverters, you will get a inverting buffer. Okay, but in both cases, 2 things will happen. One is the signal will become the perfect value. Okay, another thing that we will see later on is it will improve the timing. Okay, so this is one example. Okay, so we have seen a set of rules and a particular methodology which we can use to generate the circuit. So natural question someone might have is this the only way? Is there any other way? I have a logic function a b plus c. I have any other logic function. Is there any other way to create the circuit? Okay, and what is going to be the difference? Obviously we want some difference. If everything is the same, then we don't want that. The minimum level is functionality. That is, if I am using two different ways to create a circuit for NAND gate, okay, both have to have the NAND gate functionality. If I'm doing NAND gate and telling you this is NAND gate, then that is a mistake, right? Functionality is zero level. Okay, what other things can you change? And in particular in VLSI, the quality of a design is measured in terms of performance. Okay, and that could be again in two different metrics. One is obviously timing, delay. Okay, if it is a very fast circuit, very good circuit. If it is a very slow circuit, then it might not be suitable for your application. It might be okay. Okay, for example, many automotive applications, we have already discussed that mechanical applications are not so fast. So you don't need to be at the extreme high end of the spectrum at 7 nanometer or 5 nanometer. You could be at as low as 180 nanometer and it would still be fine for your application. So delay is definitely delay, speed. This is one. Another is power consumption. So today these are the two most important performance measures. Power consumption and area or size, okay, they are related to each other. Before they were talking about power, area, timing, but today generally power and performance, these are the two different ways to measure the quality or performance of a circuit. And power and area are clubbed. Okay, that is, if the area is high, power consumption is also going to be high. The area is low, power consumption is also going to be low. So somehow they are proportional to each other. So there is no need to separate them into two different metrics. Together we can call them as power consumption. Other one is delay. So we have listed four different logic families. They are all CMOS logic families because all of them some may, some may not, but all of them could possibly use both NMOS and PMOS transistors. In fact, sorry, they all do use NMOS and PMOS transistors because the CMOS, it's a technology or it is a fabrication process where in the same substrate we can use both NMOS and PMOS. So all these logic families, they require, okay, both NMOS and PMOS to be made in the same circuit. That is the first thing. What we have been doing so far, okay, that is pull-up network, pull-down network, dual, structural dual, etc. In particular, that is called as static CMOS logic design. Okay, that is the most common and by far it is the most popular also. And there are other options, and we are going to see the next one, which is using a different type of functionality of the transistor. It is called as pass transistor logic or transmission gates. They are both somewhat similar to each other. And in the fourth unit or fifth unit, we will see a completely different, okay, style of design, which is called as dynamic. So today, in practical situations, only two types are used: static and dynamic. Fast transistor, yes, they are used in a very small, very few class of circuits. This one, pseudo NMOS, we will look at this, but this is largely historic, and we don't use this anymore. But these two are commonly used, and these two can be used for any functionality. And the dynamic CMOS, we will mention it now, but we will discuss in more detail in the 5th unit. Dynamic CMOS is faster than what we have been doing. Dynamic CMOS is high performance. Okay, so if you have some particular part of the circuit where you want it to be very fast, you could design in this particular logic family. So we have already seen this. Next, we will look briefly at this fast transistor or transmission gate based logic design. Okay, fast transistor logic. Fast transistor logic, very simple. We have a transistor. Okay, we just want to see whether the input and output of the transistor are connected or not, and we control that with a switch. So if you have a okay, NMOS as an example, you could use PMOS also. You just want to see if the input signal goes to the output signal or not. So the transistor can pass the input or it can leave the input. And we have two transistors, PMOS and NMOS, and I will again okay, we'll make a table maybe. Okay, this table is nothing but an example of the imperfections in CMOS circuits. Okay, not in the transistor. I will never say imperfection in the transistor. Imperfections in my design. Okay, I could use in fast transistor circuits this configuration or this configuration. Okay, and assuming that the transistor is on, assuming that the transistor is conducting, if I give 0 volts as the input, in the NMOS transistor, if I use it for connecting input to output, I will get 0 volts. Good, right? No problem. But if I use a PMOS transistor, we did this analysis, it will not be able to go all the way down to 0 volts. It will get stuck at 0.5 volts. That is the problem. And here also there is a problem. If I give 2 volts at the input and use the NMOS to connect input to output, NMOS output will not reach all the way to 2 volts. It will get stuck at 1.6 volts. Okay. And how did I get 1.6, you might ask, without knowing anything? I have made an assumption. What is that assumption? I have made an assumption about the NMOS threshold voltage. NMOS threshold voltage is 4 volts. So, sorry, 0.4 volts. So at 2 minus 0.4, it will get stuck, which is 1.6. But PMOS does well. It goes to the perfect value. So fast transistor logic, directly if you use, it might create some deficiencies in your circuit. So how do we overcome? Okay, these two cases are ideal. These two cases we don't want. So the way we overcome this is, for every input to output connection, okay, put 2 transistors. That is our transmission gate. Okay, transmission gate means again it is similar to pass transistors only, but only perfect values will come. How do I guarantee that? Okay, so the pass transistor, in some ways it is enhanced. Okay, how is it enhanced? We use 2 pass transistors. Both are acting as pass transistors only, but now we have the ideal case, because if the 0 is there, okay, it will get conducted through the NMOS transistor ideally. One will get conducted through the PMOS transistor ideally. So even though the NMOS transistor will turn off at 1.6 volts, 1.6 to 2 PMOS will be conducting. It will connect the output all the way to 2 volts. So that way we can achieve the best values at the output. First thing. Second thing is, please remember the control signals. Suppose you give the same signals to both NMOS and PMOS, then what will happen? I have control given to NMOS transistor. I am giving the same signal. Here I am having a complement. But without the complement, if I give it to the PMOS transistor also, what will happen? There will be a problem. Okay. What will that problem be? Basically, the input and output, there will be a permanent connection, because if I give a signal and its complement, okay, always one of the transistors is going to be conducting. If NMOS is not conducting, PMOS will be conducting. PMOS not conducting, NMOS will be conducting. So that is why I have to give the control signal for the NMOS to conduct and control bar for the PMOS to conduct. And this is also represented by the circuit symbol, which is basically 2 triangles back to back. Okay, and the control signal and its complement. So here you can call this as, okay, and this basically is nothing but input to output connection, same as pass transistor logic, but only thing is only perfect values are propagated. So let us look at one example. Like I said in the classroom lectures also, multiplexers are the best option. So there we saw an example of 2:1 multiplexer. Let us see a 4:2 multiplexer. Okay, so 4:2 multiplexer, and basically the control signal cannot be a 1-bit control signal. It has to have a 2-bit control signal. So we can call this as the 0-0 input, 0-1, 1-0, 1-1. Okay, so sorry, that is a 4:1. So let's do 4:1 multiplexer. Okay, so for each input combination, one of the signals gets passed to the output combination. So how can we implement this using our transmission gates? Very simple. Okay, take each input combination. Okay, so basically the circuit will look like this. How many transmission gates will I require for implementing this circuit? I will require a total of 4 transmission gates. Okay, so 1, okay, and all 4 of them are connected to one single point, and that is the output. So this is 0 0 0 1 1 0 1 1. I'm not saying that that is the signal, that is the name of the input. One is the 0 0 input, it could be 0 or 1 of course. Similarly 1 0 0 1 1 1, and based on the name of the input, okay, we can give that to the, sorry, how do I give 2? I think I'm doing a mistake here. So sorry, this is not the circuit. Okay, how can I, so this is having only one control signal. One control signal, it will not go through. So sorry. How can we do it? We have to use 2 transmission gates in series with each other. Okay, not like how I had showed. Okay, so 2 transmission gates in series. Now the control is there, right? We have the control for each of them, and this could be the 0 0 input. What does that mean? That is, if this is conducting, that means that the control is, how do I give it as not, okay, let us call it as the control bits as C1 C0. Okay, and how do I give the, again here is a mistake, sorry, here I should give C0 bar. Okay, if C0 bar is given to the NMOS transistor, C0 has to be given to the PMOS transistor. So C0 equal to 0, this will conduct, and the next one here also I should give, okay, so C1 bar given to the NMOS transistor, which means that if the NMOS transistor, if the input C1 equal to 0, the NMOS transistor, and in turn the transmission gate, because I'm giving C1 to the PMOS. Okay, so if the control signal is 0 0, C1 C0 are 0 0, both will be conducting, it will come to the output. So like this we need 4 branches all the way up to 1 1. So I'll just draw the 1 1. Okay, so for the 1 1, what should I give as the control signals? I will give C0 C0 bar, C1 C1 bar. That is, if both are 1 1, both will be conducting. That is, the NMOS and the PMOS will be conducting, and that will come to the output. Also, since they are all connected, if both are 1 1, all the other 3 branches will not be conducting. This branch will conduct only for 0 0. This branch, which I have not drawn, will conduct for 0 1 1 0. Okay, and this will conduct for 1 1. So this basically is a 4:1 multiplexer using transmission gates. So each of the branch has 4 transmission gates. 4 4s are 16 transistors will be required for this implementation. Okay. So one more, this is not for example, transmission gates are a separate family of circuits, okay, and the next class is not exactly a family of circuits, but it is very important, okay, and especially when we have uh, multiple drivers for the same signal. Okay, we saw one example here, right? The 4 signals were connected to the same point. So what that means is the signal has 4 drivers, but in digital signals, of course, if I'm having 2 drivers for one particular wire, let us just see. Okay, directly this type of connection, okay, you will not see anywhere. Why you will not see anywhere this type of connection? I'm having a NAND gate, I'm having a AND gate, output of both are connected to each other. 2 reasons. One is, if the output of both are the same, right, there is no reason for 2 gates. If both the outputs are the same, you just use the output of one of the gates, you completely eliminate the other gate. Okay, that is one reason. Another reason could be that the gate's output could have different values. Suppose this gate is producing 1 and this gate is producing 0. What is the value of the actual wire, or what is the electrical signal value, right? Because one is at VDD, another is at ground. Now what is the value of the output? So it will be at a very bad or indeterminate state. So in these type of cases, when the same wire is, it is possible, okay, it is possible that this type of requirement might be there, but what we should guarantee at the design level is, if this particular gate is connected to the output, this gate should be disconnected from the output. So this will ensure proper operation. Or the other thing might happen, this gate is connected, but in that case the other gate should be necessarily disconnected, and